Bismillahirrahmanirrahim. In this session, we will discuss the variation in gas pressure with volume. The variation of the pressure of fixed mass of gas with changes in volume at constant temperature is shown in figure 2.1.11a. The close examination of the curve shows that if pressure is doubled, the volume is halved. So pressure is inversely proportional to volume. So here we can see that this is pressure. If pressure is we are increasing the volume, the pressure is decreasing. If we are reducing the pressure is increasing. At low volume, pressure is high. At a high pressure, the volume is low. Low pressure, the volume is large. So this is P, this is pressure, and inversely proportional to 1 upon V. V is the volume. So pressure is inversely proportional to volume. So this proportionality constant is equal to constant into 1 over V. So this V may be multiplied here. So PV is equal to constant. If several pair of readings P1, V1, P2, V2 are taken, then it can be confirmed that P1, V1, P2, V2 is equal to constant, and this is called the Boyle's law. So pressure is inversely proportional to volume. If we the product of this pressure and volume will always be constant. So pressure and volume will always be constant if the temperature is fixed, if temperature is constant. So this is called Boyle's law. So this Boyle's law states that the pressure of a fixed volume, a fixed mass of gas is inversely proportional to its volume. The pressure of a fixed mass of gas is inversely proportional to its volume if its temperature is kept constant. At a constant temperature, the pressure is inversely proportional to the volume of a particular fixed mass of gas. Since P is inversely proportional to V, then P is directly proportional to 1 over V. So this is 1 over V. If you plot this 1 over V, so this P and V are directly proportional. One inverse of volume is directly proportional to P. This 1 over V is directly proportional to P, but this V is inversely proportional to P. So for this is the inverse graph where we are plotting it against pressure and volume, while on the second graph we have inverse of volume with this pressure. So we have this constant straight line. So this is very important, the difference between these two graphs. This is the same data. This graph has been plotted on the same data, but here we have the volume, but here we have inverse of volume, 1 over V. So the P is inversely proportional to V, then P is directly proportional. Then if P is inversely proportional to V, then P is directly proportional to 1 over V. P is directly proportional to this 1 over V. A graph of P against 1 over V is therefore a straight line. This line. So let's put on now put this into practice from page 93. A fixed mass of gas has a volume of 9 centimeter cube. This is the volume. A fixed mass of gas at a pressure of 1 into 10 to the power 5 Pascal. Find its volume when the pressure is 3 into 10 to the power 5 Pascal. So the pressure is 3 times increases. I'm multiplying this value with a 3, so this 3 times pressure increases, so this volume will be 3 times reduced. So you can see that easily. So this the answer will be 3 centimeter cube, but we are solving it. So this is V1 and this is P1. V1 is equal to 9 centimeter cube, P1 is equal to 1 into 10 to the power 5 Pascal. V2, we have to find the V2 volume, and the pressure is 3 into 10 to the power 5. So using the equation, PV is equal to constant, we have P1, V1 is equal to P2, V2. So V2 is equal to P1, V1 upon P2. This is 1 into 10 to the power 5 Pascal into 9 centimeter cube divided by 3 into 10 to the power 5 Pascal. On division and simplification, eventually this Pascal cancel out and this volume will here, and P2 is equal to 3 centimeter cube. So this is very simple. In second question, a certain quantity of gas has a volume of 40 centimeter cube. The volume is given at a pressure of 2 into 10 to the power 5 Pascal. Find its pressure when the volume is 20 centimeter. So V1, P1 is given and volume 2 is given, and we have to find the pressure. So P1 V1 is equal to P2 V2, P2 is equal to P1 V1 upon V2, and this is here we can see that volume is half, so pressure will be double. So this is simply the 4 into 10 to the power 5 Pascal, which will eventually be the result. So I'm substituting, this is 4 into 10 to the power 5 Pascal. So this is double. The pressure is double because the volume is half. Volume is half, so the pressure will be double. Now Celsius and Kelvin temperature scales. This graph is basically the volume and temperature and pressure and temperature. So these two graphs are plotted on the same line, and on the x-axis we have temperature, on the y-axis we have volume or pressure, and the graph between the volume and temperature and pressure and temperature will be a straight line. This shows that gas expands linearly with temperature. If we increase the temperature, then its volume will increase. Similarly, the pressure will increase with the temperature. Equal temperature increases equal volume or pressure increase. So if we increase the temperature, its volume will increase, or if we increase the temperature, its pressure will increase. The graph do not pass through the Celsius temperature 0 Celsius. Here we have some points, but it is not crossing this, but so we have extrapolated it and back to here. So if we graph are extrapolated backward, then we cut the temperature axis. This temperature axis is cut down. This intercept value is at minus 273 Celsius. This temperature is called absolute zero because we believe that it is the lowest temperature possible. It is the zero of the absolute or Kelvin scale of temperature. At absolute zero, molecular motion ceases. Molecular motion becomes cease, and substance has no internal energy. At this point, substance has no internal energy. Everything will be dead. So for Kelvin scale is denoted by K, and since we know that minus 273 degrees Celsius is equal to 0 Kelvin, minus 273 Celsius is equal to 0 Kelvin. So for conversion, we can see that 0 Celsius is equal to 273 Kelvin. So we add 273 here, 273 here, it becomes 0 and it becomes 273 Kelvin. So 50 Celsius is equal to 273 plus 15 Kelvin. So 15 Celsius is equal to 273 plus 15 is equal to 288 Kelvin. So this 15 degrees Celsius is equal to 288 Kelvin. Similarly, 100 degrees Celsius is equal to 373 Kelvin. So we can say that if we have to find the Celsius Kelvin scale from Celsius scale, so this is Celsius, this is Kelvin. 273 plus this theta is showing the Celsius temperature, and this capital T is the Kelvin temperature. So this is a generic equation. We see that very high at very low temperature the internal energy shows 0, but near absolute zero strange things happen. Liquid helium becomes a superfluid. Liquid helium become a superfluid. This is the this phenomena happens. It cannot be kept in an open vessel because it flows up the inside of a vessel. It flows up inside the vessel over the edge and down the outside. Some metal and compounds become superconductor of electricity and current once started in them. Flow forever without a battery. So if we just insert some current, it will be there forever without a battery. So this is superconductor. If we decrease the temperature, it becomes superconductor. Theoretically, we say that it happens at minus 273, but in a real situation, in a practical situation, we observe it at just very much higher temperature at minus 23 degrees Celsius. It shows superconductor. So the superconductivity occurred at minus 23 Celsius, which is much higher than minus 273. Now put this into practice. We have given 80 degrees Celsius to Kelvin. So this is the formula. T is equal to 273 plus theta. Theta is a Celsius temperature, so we put 80 here, and this 80 degrees Celsius is equal to 353 Kelvin. Similarly for 100 Kelvin, so this is 100 Kelvin, 273, and we have to find the Celsius. So this theta is equal to 100 Kelvin. This becomes here, and minus 173 degrees Celsius. So 100 Kelvin is equal to minus 173 Celsius.